we're drawing Lewis dot structures. And I think right before we left, we were just about to look at the formal charges on our resulting molecule that we had for HCN. Okay, so let me catch us up. I'm going to go through this and we're going to rewrite the Lewis dot structure for HCN, cyanic acid, okay, or hydrogen cyanide if it's not in water. Okay, so we're going to rewrite it. As we go down the list over to the left, I'll be asking questions to see if you remember. This is a little bit of review, so if you don't remember, you just say, I'm sorry, I don't remember, and then I'll ask the next person. So please be ready to answer the questions when it comes to you. Aisha will be the first one. She's always at the top. I guess they're organizing this alphabetically. I never realized that, but I guess that's what's going on. Okay, so here we go. Drawing a Lewis dot structure, the first thing is to recognize the central atom. Aisha, how would I choose the central atom for HCN?
This is the most electronegative one.
Okay, it's actually the least electronegative. It's the least electronegative that wants to be the central atom. And there's also some things to remember. Some of the things to remember is that if carbon is there, it says always here, and it depends on your definition of central atom, but because carbon has need of lots of electron density, right, 4 valence electrons, then it's almost always, if not always, going to be a central atom. And then hydrogen is always going to be terminal because it can't bond more than one thing. All right, so very good. Alyssa, then what's my next step after I've identified the central atom? What do I draw here?
You can draw how many valence electrons each has.
Okay, we can make a list of the number of valence electrons. Like carbon has how many?
It has 4.
4 valence electrons. Very good. Nitrogen, how many, Alyssa?
5.
5. And then hydrogen?
1.
1 valence electron. Very good. So that tells us how many total valence electrons. Very good. Anastasia, what do I draw after I have recognized my central atom as carbon? What do I write down here?
That drawing the Lewis structure.
That's right. So I draw a carbon, and then what do I do?
And then connect it to hydrogen and nitrogen.
That's right. Very good. So I draw my central atoms and then my outer atoms bound together with a bond. Very good. Okay, now Brielle, we've already got our 10 electrons here that we added up. What's my next step, Brielle?
You subtract the valence electrons that are in the bonds.
Very good. Very good. 4 valence electrons, 2 in each of these bonds. So now I have 6 valence electrons left over. And Camilla, what's my next step with those 6 valence electrons? Where do I go first?
Start with the central atom.
Central atom, that's right. And how much electron density does it need, Camilla? How many more electrons do you think I need to put on that central atom?
Well, it only needs 4, right? Or no, it wants 8. So, you need 2 on the top and on the bottom of it.
Very good. So now it has access to 8 electrons. 1, 2, 3, 4. This bond it has access to is 5, 6, and then 7, 8. Very good. I've used up 4 electrons. My next 2 electrons would need to go on nitrogen, right? So now I'm out of electrons. Okay, so something needs to be rearranged, Camille. What do I have to rearrange? How can I rearrange, Camille?
I
See if this reminds you of something.
Oh, would there be more in the bond then?
Yes, that's right. So I take these non-bonding electrons and I form them into a bond, right? So what that does is it makes those two non-bonding electrons available to both the carbon and the nitrogen now, right?
Yes. So would you do the same thing with the other two?
How did you know to do the same thing with the other two? How did we know? Because here, we still don't have enough electron density for the nitrogen, do we?
No.
1, 2, 3, 4, 5, 6. So we need these other two to come in and form another bond. Okay, very good. Now, I can see that carbon has access to how many electrons chance?
8 electrons.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8. And that nitrogen, does it have 8 also chance?
Yes.
Yep, and then hydrogen has access to 2 electrons. Very good. So, Chance, do you remember what has to happen next to kind of verify that this is a correct structure? It's the formal charges. Do you remember what formal charges are? What that means?
Oh, is that just trying to remember. Is it just like the number of the bonds plus the number of shared or unshared? Or like it's an equation? I don't remember the equation.
Okay. So what we're trying to measure here is the number of electrons that are right around our atoms, right? Right around our atoms compared to the number of electrons they brought. And the story to help us remember that is like when you go to a party, right? What do you bring to the party, Chance?
Snacks.
Snacks. That's right. Everybody brings snacks to the party. But when you bring snacks and nobody else brought snacks, then what's your attitude like?
Not very happy.
Yeah, you want to make sure that you don't lose access to your snacks or your electrons that you brought. So we see that carbon brought 4, nitrogen brought 5, hydrogen brought 1, right? These are check marks there. So we need to make sure that those are the same numbers, 4, 5, and 1, respectively, that the atoms have right around them, okay? So do you remember how to determine how many electrons are right around that carbon, Chance?
Is it just adding up the bonds?
Yeah. So this bond, all these bonds act like 2 electrons, and you can think of them for this calculation as 3 available, or sorry, 3 that are right around carbon on this side and 1 that's right around carbon on the other side. So a total of 4. You see that? See that okay, Chance?
Yep.
Okay. Chloe, how many electrons are right around nitrogen?
5.
5. That's right. 1, 2, 3, 4, 5. Okay. So how do we calculate their formal charge, Chloe? Do you remember?
Yeah, you do how many they brought minus how many are around it.
That's right. So carbon brought 4 minus how many are right around it? 4. So that's a formal charge of 0, right? Nitrogen brought 5 right around it. So the formal charge is 0. Hydrogen brought 1 right around it. Again, formal charge of 0. So this is an indication that this molecule is stable and a likely structure, likely candidate for this compound. Okay?
Brother Scott, I have a question.
Yeah.
How do we know that both carbon and nitrogen needed access to 8 valence electrons?
All right. Let me get my periodic table out here. Just a second. Let me see where we are. We need to bring this up. We need to bring this up. This up again. Whoops, what happened there? Okay, there we go. All right, so essentially, all of our atoms in this vicinity, right, have some number of valence electrons, right? And we can identify the number of valency electrons by counting its column. 1, 2, 3, 4, 5, 6, 7, 8, right? And for stability, atoms will come together in compounds so that they can fill their outer shell, right? Fill their outer shell. So here's selenium, for example. It has already, in terms of valence electrons, 1, 2, 3, 4, 5, 6, and it wants to have 8, like krypton. So that's how we know it wants to have 8. All of them essentially will always want to have 8, except for one exception. What is it, Catherine?
Hydrogen.
Hydrogen, that's right. A hydrogen will only want to have 2. Did that answer the question or not? Okay, that's fine. Okay, very good. So, Lewis dot structures that have formal charges of 0 after we're done drawing them are again indications that they're the correct Lewis dot structure. All right, so let's try to draw the Lewis dot structure for carbon dioxide. Well, let's see. Okay, let's draw the Lewis dot structure for PCl3. All right, we're going to draw the Lewis dot structure for PCl3. We're going to do this in our breakout groups. All right, so please share with your neighbors and work together to try to do this. Let me see. There we go. So some of you will only have 2 people in your neighbors or in your little breakout group. So make sure you join your breakout group, okay? And we're going to draw the Lewis dot structure for PCl3, okay? Okay, go for it.
Board.
Okay. Thought I did. I don't see the thing on the. I don't see it.
Do you know how to do this, Kylie? Kylie has to do it. She's the presenter, apparently.
Wait, how do I do it?
Is there a little thing over to the right here? Let me take the presenter and see. Yeah, so after you the presenter, there's a little something that shows up over here. And now I think everybody should be able to write. Is that true?
Oh, whoa. Word.
So unfortunately, we have to have that dumb background. I don't know why that's the case, but yeah, you guys work on this. I'm going to leave and go make sure other people can get the thing working, okay?
Okay.
So Kylie, I'm going to make you the presenter, all right?
Okay.
So there should be like a little tab that shows up, and the bottom button is the one to make it all public. Okay.
The 24 left since we just wrote down 2, or do we subtract the bond?
Yeah, those are part of them too.
You're right, I don't forget. So,
Daisy,
you're right. Yes.
see how you're the presenter? There's a little computer on your little insignia on to the left there.
Oh yes.
That means that there's a little tab, and you can, on the bottom, make that so that everybody can write, and then you guys can draw on that. There you go. So now you can draw the structure right there. Does that make sense?
Yeah.
Okay, cool.
So make sure you choose a pencil at the top right there. Very good. Okay, I'm going to leave and go show other people. Bye-bye.
Okay. Thank you.
other electrons right around phosphorus?
Joey,
Yes.
you see how you are the presenter on the left there? It gives you the little computer signs showing you're the presenter. That means there should be on the left the list of users.
Okay.
There should be a little bar to the right of the screen right to the right where it says emojis, multi-user whiteboard, and you should be able to click on that bottom bar, and then other people should be able to actually draw what we're talking about on the screen. You see that, Joey?
Oh. There's a bar that I click on.
To the right there.
Okay.
Here, let me. I'll take the presenter, and then I'll open it up
Okay.
for everybody. So now everybody, we can draw. Whoops! If you go to the top right and choose a picture, let's see, is this? There we go. Now it's on. Does everybody turn? Oh, here we go. Now it's on. Okay, there we go. So now we can draw carbon, and then we can start working from there. Does that make sense?
Yeah, thank you.
Okay, so whoever's going to get that little computer to the top left, I'm going to leave. Make sure it stays available to everybody so you can draw it. Okay, see you in a bit.
Thank you.
Mhm.
In this conference.
All right. So PCl3. PCl3. Did you guys get it? Let's see. Where did we leave off? Was it Ephraim's turn? Let's see. Ephraim doesn't look like he has a microphone on, but tell me down below. Did you get it? Yes or no, Ephraim? No? Okay. So, and who was in Ephraim's group? Anybody in Ephraim's group? Ephraim, did you have people in your group?
I never had a turn, and I think it would be me actually because I'm after Chloe.
Oh, you got skipped?
Yeah.
Okay.
I think I did it right too. If you want me to try.
Excellent. Sounds good. Do you want to have the whiteboard so we can all watch what you do?
Sure.
Okay, there it is. So give her some space. There we go. So talk us through what you did, why you decided what to do. Why did you decide to put the phosphorus in the middle?
Because it is the least electromagnetic.
Electronegative. Very good.
That's what I meant.
Another reason that we kind of know is if it's the only element of its kind, then that's almost always a guarantee that it's going to be the central atom. Very good. So what did you do after you have your skeleton molecule drawn?
Then there was 5 phosphorus brought to the party.
Mm-hmm.
Well, you could say party.
Sure.
And then there was 21 chlorine.
Electrons from chlorine. Uh-huh.
Oh, that's a 2. Okay. So then.
Hold on just a second, Daisy. Everybody get ready. As soon as Daisy tells us to decorate the electrons around the chlorine, we'll all do it together, okay? So everybody get ready. Go for it, Daisy.
Okay, so we're gonna minus the bonds. So -4.
Okay, why did you choose to subtract 4?
I'm at 6.
Okay, all right. And you got 6. Why did you choose to subtract 6?
Because there's 3
Okay,
bonds.
all right, excellent.
Right, I'm at 6. Okay, and then that gives us 20. Oh, I'm gonna run over. And then you want to start with phosphorus, and so that only gets 2.
How did you know it only
Yes,
needed 2? Okay, good. Go for it.
Okay, and then.
So tell us again, how did you know it only needed 2?
Oh, sorry. Because the bonds each count for 2, and it wants to be 8. So this is 2, 4, 6, and then you need these 2 dots to be 8.
Okay, so it has access to 8 electrons now. Good.
Yes. Okay, so then we need 18 electrons, and then we have 3 chlorines, so then we need 6 electrons on each chlorine.
All right, everybody, fill it up. Go. Very good. Excellent. Now, Daisy, did you have a chance to identify formal charges on this compound?
Yes. So we saw that chlorine brought 7 to the party. Do you want me to write it down, or do you want me to just talk it?
Why don't Catherine, you write it for her. You be her scribe as she talks it. Is that okay, Catherine?
Okay.
There you go.
So we saw that it brought 7 to the party, and then we saw the ones that are close around to it, around all the chlorine things is 7. So then it's just a 0.
Okay.
And then same with phosphorus, it brought 5 to the party, and then there's 5 around it. So it would also be 0.
Kylie, can you circle the 5 electrons that are right around phosphorus? How we're representing those 5 electrons? Where are the 5 electrons, Kylie, that are right around phosphorus?
The 5 around phosphorus?
Yeah, she said there were 5 electrons around right around phosphorus. Where are those 5 electrons?
I have no idea.
Okay, Anastasia, can you circle those 5 electrons that are right around phosphorus?
So this 2 of them,
All right,
and then there's 1 here,
good. 3,
1 over here, which is 4, and then 5 on this end.
very good. That's how you can tell there's 5 electrons. That's how you identify the number of electrons around an atom. The lone pair ones and then the bonds always count as 1 electron. So no formal charges on anything. It's a good sign that this is the correct structure for the compound. Okay, very good. So let's draw carbon dioxide together. Okay, now there's multiple ways to approach this, but I'm going to follow our rules that we've set forth, and I think it's always safe to follow these rules. If you get kind of stuck into a corner somewhere and don't understand exactly how to distribute your electrons for some reason, it can sometimes cause problems. So it's just best to follow the pattern that we have set forth already. So we're going to do this here with carbon dioxide. Central atom, carbon. Draw my oxygens. Count up my electrons. Let's see, Ephraim, can you count up the electrons? How many electrons are brought to this party here? 4. Carbon brought 4. Very good. So the oxygens, how many did each of them bring, Ephraim? Okay, so we can tell how many electrons are brought by the elements based on the column that they're in. So this is column 1, column 2, column 3, 4, 5, 6, 7, 8. So because carbon is in column 1, 2, 3, 4, I know carbon brought 4 valence electrons to this party. Okay? And because oxygen is in column 6, I know that each oxygen is going to bring 6 electrons. So that's a total of 16, 12, 30, 40, 50, 16. So I have 16 valence electrons. All right. Okay, Joey, how many electrons are on the table already or on my skeleton model?
4 total.
All right. And then Catherine, where do I put my next electrons?
Would you put 2 on carbon?
All right, at least 2, right? Now carbon has how many electrons available to it currently?
Oh, wait. So it already has 4 available. So put 4 more.
2 more on top to give it an additional 2. Very good. So 8 valence electrons left. I'm going to try to put them maybe 1, 2, 3, 4. I don't know. Should I go 5, 6, 7, 8? Something like that. Out of electrons, but not everybody has 8 electrons available to them. True? Who doesn't have 8 valence electrons available to them? Who is it? Quince? Is it Kylie? No. Let's see. Catherine. Kayla. How many, who doesn't have 8 valence electrons available to them? Oxygen 1, carbon, or oxygen 2? Oxygen 2, that's right. It only has 1, 2, 3, 4 valence electrons. So what can I do to increase the amount of electron density, Kylie?
I have no idea.
Okay, I need more electron density around this oxygen, right? I need to have 8
Yeah.
electrons available there. And I can take these electrons and move them over there, right? Because when I take non-bonding electrons and make them as shared electrons, then oxygen now has those electrons available to it. Does that make sense?
Yeah, so then would you just draw another line right there and take away the...
That's right. So you kind of have to start over if you're drawing in pen, right? But that's where we would be at after we made that decision to move those electrons. Kylie, you want to keep going? What is it? I mean, are we done yet? Does oxygen now have 8 electrons available to it?
No, I only have 6.
Only has 6. So,
Could you do 3 right there?
yeah, and we can bring those electrons in like that. Now I have 1, 2, 3. And the question of, is that legal? Is that okay? That question will be answered by the formal charges. All right? So now we have a setup here. Quincy, how many electrons are available to this carbon, Quincy? I'm going to type it in down below. Rebecca, how many electrons are available to this carbon?
8.
8. And this oxygen, Rebecca?
8 also.
And here as well. True?
Yes.
Okay. So now the question is, do we have a finished structure? And what's going to tell us, Rebecca, whether or not we have a finished structure?
We have to find out how much they had initially,
Yeah.
or how much they're sharing, or like around them also.
And what's the fancy term for that? Do you remember?
I have it written down as FC. I forgot what it was.
Very good.
Yeah.
Formal charges. Very good. So we need to calculate the formal charges. Can you calculate the formal charge for the carbon for me? And Sarah, why don't you calculate the formal charge for this oxygen? And Zaf, why don't you calculate the formal charge for that oxygen? Let us know, Rebecca. What do you think? What's the formal charge here on the carbon?
It brought 4 initially, and it has 4 around it, so it's 0.
Very good. 4 minus 4. So carbon is in a good place, right? That's a good setting for itself. Sarah, let's see. That was Rebecca, right? So Sarah's turn. What's the formal charge? Did I tell you the right or the left?
I have the left.
All right. What is it?
So it only brought 6, but it has 7 around it. So that'd be -1.
Yeah, -1. And that negative sign there, I'm going to circle this 0 as well, so I'm circling all the formal charges. That negative sign is an indication that there's too much negative charge, too much electron density around this oxygen. Okay. Zaf, did you get to identify the formal charge here? What's the formal charge on that oxygen? You can type it down below there. -2. Let's see. How many electrons did this one bring, Zaf? How many electrons did oxygen bring? Okay, so let's look at our periodic table. We can tell how many electrons were brought to the party by the different elements based on the column that that element is in. So because it's right here, how many electrons did it bring to the party? What do you think, Zaf? Okay, so what we do to determine how many electrons were brought to the party, we look at their location on the periodic table, and we count the columns of the representative elements. So this is 1, 2, 3, 4, 5, 6, 7, and 8. And because oxygen's in the 6th column, it brought 6 electrons. That's right. So it brought 6 electrons, and now we have to subtract how many electrons are right around that oxygen. Do you remember how to identify how many electrons are right around this oxygen here? Remember how to do that? How many electrons are right around this oxygen? Answer again. There you go. Yeah, go ahead and answer again. All right, very good. It is 5. 1, 2, and then 3, 4, 5. That means the resulting formal charge is 6 minus 5, or a positive 1. And that positive sign, what do you think that positive sign means, Aisha? What is the negative sign meant something, and so the positive sign means the opposite, Aisha. What do you think? What is that positive sign meaning?
The -1 means there's more electron density around it. So the positive one less.
Yeah. Positive 1 is indicating to us that it needs more electron density. More electron density.
So positive 1 means more?
It means, no, it means it needs more. It doesn't have enough negative charge. Just like with atoms, these are like not full charges, but they're an indication that electron density is lacking here and there's too much over here. Okay? So, very good. Now, Alyssa, we have a tool available to us to increase electron density over here. We have a tool which is taking these bonds and moving them into non-bonding electrons on the oxygen. Okay? So if we do that and we rewrite our new structure up here, these bonds now become non-bonding bonds around the oxygen. Okay, so we move the electron density over here. Alyssa, how many electrons does this oxygen have available to it now?
It has 6 available to it now.
Let's see, 1, 2, 3, 4, 5, 6.
Sorry, I thought you meant for formal charge.
But that's good too. Has 8 available to it, but it's has 6. What do we say? Not available to it, but right around it. Is that right?
Yeah, so as the formal charge is 0 now.
Very good. So we're done with that oxygen, aren't we? Did we do anything wrong with this carbon, Anastasia? Is this carbon in a good place? Can we stop with this carbon, Anastasia?
No. Because right now, carbon is only accessible to 6
Okay.
billion.
So what can we do to bring in more electron density to the carbon? Should we bring these electrons back?
No. Maybe 2 from the other oxygen.
Very good. We bring in 2 from there, and then that gives us this structure. Now, we can see here that these oxygens are the same, and Alyssa just told us that this one has a formal charge of 0, so that one's going to have a formal charge of 0. Brielle, can you tell what the formal charge is on the carbon now?
Now it's 0.
Now it's 0. Very good. So we got it. We got our Lewis dot structure, and this is telling us what our chemical structure for carbon dioxide looks like. Very good. So this is very helpful, and we'll talk about in chapter 10 here coming up why these Lewis dot structures are very helpful to us to tell us about the properties of the compounds. Okay. In some scenarios, we have what's called an expanded octet. Expanded octet. Now, this can only occur when you're talking about elements in the 3rd row or lower. So for our nonmetals, it would really be elements like phosphorus, sulfur, chlorine, argon, selenium, bromine, right? All of these down here. When they're in the 3rd row, they have available the 3rd shell, which contains d electrons. And so you can have more bonding occurring than just the typical 8 electrons in a valence shell. So you can have what's called an expanded octet. Okay? Now, let's see if this video works. This is a cool video here.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds
Can you guys hear that video?
Yes.
Okay, excellent.
higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and my voice gets really low, although somehow I'm still funny. It's scientific!
Okay, so did anybody catch it? What was he breathing there? Sulfur hexafluoride. Sulfur hexafluoride. Okay, why don't you all individually try to draw the Lewis dot structure for sulfur hexafluoride? Okay, everybody can work on it individually, and we'll talk about it in a few moments here. Okay, I'll give you about a minute and a half to work on it. All right, so right off, you can probably see that just to draw your skeleton structure, sulfur is going to need to have more than 8 electrons available to it. Okay, so this isn't a problem for sulfur, why isn't it a problem for sulfur, Camilla?
Well, when I did it, each F still got 8 electrons, and it worked out fine, and then it was still added up to a total of 48. So, I think it works.
Okay. 36 electrons left, right? So we can see that each one of these is going to have 6, because there's 6 times 6, 36 electrons. But why is it okay for sulfur? How many electrons does sulfur have access to, Camilla?
12.
12. Why is that okay?
I don't know, actually.
Okay. And it's this new idea of what we call an expanded octet. So because sulfur is in the 3rd row of the periodic table or lower, that means it has elements. This is our 3p. And as the 3p fills, those 3d electrons, those orbitals, are available to these elements. And so additional space in the 3d orbitals allows for extra electron density. And in chapter 10, we'll talk about where that is actually going and how that's actually working out. But we can have expanded octet for elements that are 3rd row or lower. Okay? So let's watch one more cool video with this, what this sulfur hexafluoride can do. So what we see is no formal charge on the sulfur, right? It brought 6 electrons, has 6 right around it, and no formal charge on any of these fluorines. And we have a very symmetric molecule, Now we're drawing these things in 2 dimensions. But if you think about an X, Y, and Z axis, you can think about these on our Y axis, these on our Z axis, or on our X, and these on the other one, right? And what you would have here is a very symmetrical molecule. And because the molecule is very symmetrical, even though it contains fluorine, if you breathe fluorine gas, you die, and sulfur, not something to just breathe by itself, the resulting molecule is very inert and not, you saw that he could breathe it, right? So here's another video here. It's kind of a newscaster. They have this box filled with the sulfur hexafluoride. I'm going to take the lid off of the box, and then he's got a little boat made out of some tin foil here, and he's going to put that boat on top of the sulfur hexafluoride. All right?
That is awesome. So this heavy gas is about 6 times heavier than the air that we breathe. And so I just have it coming through a tube here, and so I'm going to give us just a little bit more so you can see what's going on. Here's what they use it for. Electrical engineers will flood a room or part of a semiconductor or something with this material because it doesn't allow electricity to, it doesn't conduct electricity. So here's a taser. Okay? So all right, so look, here's the taser. So when I put the taser down inside here, watch this. So it's down inside. It stops working. And now when I bring it back out again. Oh, wow. So they will keep it so if you don't want something for arcing from one place to another. But the coolest thing is this. Because it's inert, you can breathe it, and you might see something different. Ready? So, can I go first? So just stick your head way down inside and breathe in. Breathe in. Ready? Now talk to the nice people. Try it. Come here. Get in there. Awesome.
All right. So, same thing, right? But new material, different properties. Like he said, when you're making semiconductors and doing electronic work, you don't, especially in factories, you don't want to have stuff blowing up, right? And so the use of this type of new material really resulted in made a lot of things possible that weren't possible before. And that's what chemistry is about. It's about recognizing materials that can do stuff based on their Lewis dot structures, or understanding their structures, understanding their properties that they'll have. Okay, so Let's see here. Here are some structures that we could probably pull off pretty straightforward. Let's talk about this one. XeOF4. I think this is where we'll stop. We'll come back together again in class and we will work on some of these. And then, let's see, we have one other. Yeah, that's it. So next class, we'll be able to finish up and then we'll start into chapter 10. Okay. It doesn't look like we're going to be able to go past chapter 10. So we'll be getting into chapter 10 and that will be it. We won't be getting into chapter 11 for the final exam. Put a little yes down in the chat box if you're going to be taking Chem 106 in the spring. Put a little yes down there in the chat box. Okay, so I'd like these people to hang around and I'd like to have a discussion about how you would like to proceed in Chem 106, especially because we're going to have to be doing it in a similar format, or we have the ability to choose what kind of format we want. And if there's no proof in my experience that people can learn chemistry like this. I mean, if we could learn chemistry like this, there are so many different videos online like this already. So there's more to it. There's more of a connection between the professor and the eyes of the students to make sure they're understanding what's going on. There's more of a need to ask questions and so forth. So I'm not convinced that this is something that can actually work. I think in the end here, we're just going to kind of finish up and that's that. We can move forward and try it this way and do whatever, but I'd like to get your feedback. So everybody who is going to be here in Chem 106, please hang around. We'll talk just for, maybe hopefully less than 5 minutes. Everybody else, you could stay here, but, don't contribute a ton of information if you're not going to be the one who's going to have to follow the suggestions during spring. All right. Yeah, go ahead.
I was planning to take Chem 106 at a later date when I could take it in class. Is that going to affect me because we are cut short and we didn't get to chapter 11?
If it would just be chapter 11. And there would be probably 3 or 4 questions on an exam, a cumulative exam that contain chapter 11. So you'd have to do some sort of catch up. For the spring, obviously, I'm going to pick up right where we left off. And for my fall class, well, that's 105 again. Let's see what would. It's just hard to say. Okay. Some classes don't get to the gases chapter. Some classes do in terms of other universities. So, yeah.
Thank you.
Yep. So, any other questions?
Me, but not about 106.
Okay.
What is exam 4 again?
Well, we're just going to have the final exam. We're not going to have another exam. We have a practice exam online, which I think is a good representation for chapter 1 through 8 problems. And you should be working on that, trying to get good at those problems, understanding them, working with the tutor to work through those, asking me questions about them. And then chapter 9 problems will be added to that. And then we're going to have our final. Our final is going to be hopefully open April 16th. Let me see here. April 16th. And it might be open April 15th and probably be open until the 20th, but maybe just the 18th. So you're going to have a window of about 3 or 4 days to take it. But does that make sense, Anastasia?
Yes, thank you.
You bet. Okay, any other questions before we talk about 106 format? So I have 1, 2, 3. Where's my mouse? Let's see, 1, 2, 3, 4, 5 people who are planning on taking 106. Alyssa, do you have any feedback for what you would prefer to see? Different, same, or would you prefer someone else talk?